We're now going to work through one small example to verify whether the theorem of Rolle is valid for the function fx is equal to x into x minus 1 into x minus 2 in the interval 0 to 2. Now, as a solution, we might say, the first condition is that the function fx must be continuous in the interval. Here we see that the function fx is nothing but, if we simplify this, is actually x into x square minus 3x plus 2. In other words, this is equal to x cubed minus 3x square plus 2x, which is of course a polynomial in x, and all polynomials are continuous in the entire real axis. So there is no doubt that this function is continuous and the condition of continuity is satisfied. Now, about the second condition is the condition of differentiability. Now, if this is fx, we can say that f dash x is 3x square minus 6x plus 2, and this exists for all real values of x, and hence the function is differentiable in the open interval 0 to 2 because it is differentiable for all values of x. So the second condition is satisfied. Third condition says that at the end points, the value of the function, that means fa and fb, must be equal to each other. Now, f of 0 is 0. F 0 is 0, and f of 2 is nothing but 2 cubed, that is 8, minus 3 into 2 square, so that is 8 minus 12, plus 2 2s are 4. So 8 plus 4 is 12, minus 12 is 0. So f2 is also 0. So there we are, we've seen that all the conditions of Rolle's theorem are satisfied. Hence, we assert that there must be a value of c, at least one value of c, between 0 and 2, such that the f dash c becomes equal to 0. In other words, at those 2 points, the tangent drawn to this graph will become parallel to the x-axis. We now proceed to find and see if we can find out a value of c that does indeed make f dash x 0. So we just have to focus on this equation. Now, for f dash c to be equal to 0, we must have f dash c is nothing but 3c square minus 6c plus 2. And if we equate this to 0, that would imply that c is minus b, that is 6, plus minus square root of b square, 36, minus 4ac, 24, by 2a, which can be simplified to 6 plus minus 36 minus 24 is 12. If we take the square root of 12, 4 into 3, we will get 2 root 3. So this works out to 6 plus minus 2 root 3 divided by 2 into 3. We can make that collapse to 3 plus minus root 3 divided by 3. That is equal to 1 plus minus 1 by root 3. Now 1 by root 3 is 10 by about 17. 10 by 17 is about 0.6. this will have a value of 0.6. So one value is 1 plus approximately 0.6, so that is 1.6, and the other is 1 minus 0.6, and that is 0.4. So the two values are approximately equal to 0.4 and 1.6. Both these values we will observe lie between 0 and 2. So this is a situation in which we have two C's and each of them lie between 0 and 2. So that drives home the point that for this particular function, which is x into x minus 1 into x minus 2, in the interval 0 to 2, the Rolle's theorem is valid, the conditions are satisfied, and we have indeed demonstrated that there are two values of C which lie between the endpoints of the interval 0 and 2. Now, while talking about the mean value theorems of Rolle and Lagrange, there is one important aspect, and this has to be explained very carefully, that the C which lies between A and B, both in case of Rolle's theorem or Lagrange's mean value theorem, can be written in a different way. In other words, C is equal to A plus theta into H. We will explain these terms. Now, we have said that C lies in between A and B. So, we have taken on the x-axis just the x values. This is the x-axis. We have taken an x value of A, x value of B, and C is squarely in between A and B. Now, if we care to give the difference of B and A, this interval, as H, we call it H, then we see that C has to be evidently A plus this portion. This is the additional amount to be added to A to get C. So, C is equal to A plus, you can't take the entire interval. We have to take a fraction of this interval so that we arrive at a value of C that is inside A and B. So, this fraction theta has to be between 0 and 1. So, this gives us a very nice way of writing the value of C as A plus theta times H, where theta is a number that is between 0 and 1. Theta cannot be 0, theta cannot be 1. We will see what happens if theta is indeed taken as 0 or 1. Theta is essentially between 0 and 1. Now, let us be a little careless and take theta as 1. Then we say that C is equal to A plus 1 into B minus A. If we take A plus 1 into B minus A, we get B, and that is coinciding with the end point, the right end point. That's not allowed because C has to be inside. If we take theta as 0 here, then C is equal to A, that is the left hand side point, and that is also not allowed. So, we are convinced that theta has to be between 0 and 1. We will write Lagrange's mean value theorem in a different way using different notations, because the theorem can be written in various ways, many different ways. One of them we will see. Now, supposing we get back to the theorem that we had written in the very first instance, we had said that in the case of LMBD, Lagrange's mean value theorem, FB minus FA over B minus A is F dashed C. Now, if we just use the terminology used just now, introduced right now, then supposing we say that if B is nothing but A plus H, A is of course A, B minus A is H, then this theorem can be written in the following form: f of b is a plus h minus f a over b minus a, that is h, is equal to f dashed a plus theta into h. In other words, f a plus a h minus f a is h times f dashed a plus theta h. So we write that, or in other words, f of a plus h is equal to f a plus h times f dashed a plus theta h. This is another way of writing Lagrange's mean value theorem. Once we understand the basic symbols and terms, it's very easy to write down these forms in a different way. One more point, for example, if we take b as x, any point, a as 0, that means a as the origin, the x coordinate of the origin, then the theorem can be written like this. We love out this part and get another special. These forms will come handy when expansion of functions is being discussed. So let us choose special case. B is represented as a general value, x, which is a floating value. A is taken to be 0, that means the point of the origin. Then this whole theorem becomes fx minus f0 over b minus a is nothing but x is equal to f dashed 0 plus theta times b minus a, which is x. In other words, fx can be represented as f naught plus x times f dashed theta x, keeping in mind theta is less than 1 and greater than 0.